In this video, we are going to attempt to establish some type of a procedure for choosing a convergence test. There's lots of different resources out there for what to look for when you are trying to choose a test for determining convergence. And this is just one of the options. I have a nifty little cheat sheet type flow chart, which I will attempt to get posted as soon as I get it scanned. I will post that into more. So read over this problem-solving strategy and see if it makes sense, or you may develop your own type of a strategy. But choosing an appropriate test is important because you're going to be given a bunch of different series and just told to determine if they're convergent or divergent. So let's just take a look at a few. So in this one, I notice that, well, it's a rational function. I have a polynomial in the numerator and a polynomial in the denominator. And so with polynomials, what's really important is the leading term in each, in the numerator and the denominator. So essentially, if you just look at the leading terms, you have n squared over n cubed, which kind of reduces to 1 over n. So I'm thinking, well, why don't we compare it to 1 over n? So that means we're going to use one of the comparison tests. But which one? We have two of them. There's the limit comparison test, and there's the direct comparison test. Well, the direct comparison test says, so this is a diverging harmonic. Our comparison test is a diverging harmonic. So the way I like to look at it is if my harmonic is diverging, and this isn't necessarily the function of 1 over n, but let's just say this is a diverging function. If it's diverging, then the other function, a sub n, has to be above it. Okay, it has to be above it. Because if the green line is going up further and further, and it's diverging, then a sub n has to be above that all the time, and so then it would also be diverging. If that was below it, then as the green one goes up, we don't know what this is doing down here. All right, so in other words, a sub n has to be greater than b sub n because b sub n is diverging. So again, this is going back to the direct comparison test. Well, when you check to see if this is true, it's not. So you can't use the direct comparison test, but you can use the limit comparison test. And so let's take a look at the limit comparison test. So the limit comparison test says we take the limit of the ratio of a sub n over b sub n. Okay, the limit of the ratio of a sub n divided by b sub n. So that's what we've got here. Well, simplifying all of that, we end up with this. And applying a L'Hopital's rule 2 or 3 times, or just by looking at this intuitively, again, the leading terms are n cubed over n cubed. As n gets infinitely large, and you have a polynomial function in the numerator and a polynomial function in the denominator, the only term that matters is the leading term, the highest powered term. Everything else becomes inconsequential. So n cubed over n cubed is 1. And so if you apply L'Hopital's rule, or if you divide everything through by 1 over n cubed, no matter how you do it, you're going to find that the limit is equal to 1. So remember what the limit comparison test says. The limit comparison test says that if there is a limit, if the limit exists, then both series either converge or both series diverge. Since we know that this is a diverging harmonic, then the series that we are looking at right here also diverges. So this is a good one for the limit comparison test. Next one looks rather complicated, and we also notice that it is an alternating series test. So whenever I see an alternating series, I'm immediately going to either the ratio or the root test. That tells me if it is absolutely convergent or not. All right, so we just did the ratio test. So we want the ratio of a sub n plus 1 over a sub n. And so that's what we have here. And so -1 to the n plus 2, we can break up into -1 to the n times -1 squared. Taking all of this and doing a little bit of algebra on it, we get 3n plus 4. We know how to take n plus 1 factorial and divide that up into n plus 1 times n factorial. And now we can just do some canceling. The n factorials cancel. The -1 to the n cancels. These -1s just go away. They're positive or -1, and the absolute value of that is going to be positive 1. And so what we are left with in the numerator is the 3n plus 4, and in the denominator, n plus 1, 3n plus 1. So that's what we've got here. So taking the limit of that, if you were to multiply the denominator, the leading term of the denominator is 3n squared. So again, if you do this intuitively, or if you use L'Hopital's rule, or if you just go through and divide everything through by the highest powered term, you're going to see that the limit is 0. And 0 is less than 1. So the series converges by the ratio test. Okay. And the next one, want to use the divergence test. So you look at this, remember what the divergence test says. If the limit does not equal 0, then it diverges. If the limit does not equal 0, it diverges. And so the limit does not equal 0. How do we know that the limit doesn't equal to 0? Well, you could try doing L'Hopital's rule a few times, but let's just look at this. E to the n is going to get bigger faster than n cubed is. And so the numerator is getting larger faster than the denominator. And so it's approaching infinity. So the series diverges. If the limit of the series does not equal 0, then it diverges. It doesn't, so it diverges. And the next one is a root test, and that's the last one. So this one is clearly made for the root test. All right, so we see that 3 is being raised to the n plus 1 is both raised to the n. So that's just screaming for me to do the nth root test, because we know those n's are going to cancel out. We're just going to end up with the 3 over n plus 1. And the limit of that is 0, which is less than 1. So the series converges. All right, that is it for this video.